לך איברים מעורבים גם.
נכון.
אז לא, זה לא I, זה J.
נכון.
סבבה. עכשיו האלפות הם לא תלויים. נכון?
אלפא אבל הם בתוך הסכום, אתה לא יכול להעיף אותם מחוץ ל...
לא, שנייה, אז אני עושה אותם סכום כפול על IJ, אלפא I, אלפא J, J, זה I, זה J, נכון?
מה עם אחד ג'?
מה? צריך להיות בתחום באלף. זה נכון? אתה הופך את זה סכום כפול?
מה אתה חושב? זה הכל כקומבינציה לינארית של ה...
כן. עכשיו יש לי ממוצע של סכומים, אני הופך את זה לסכום של הממוצעים ואני יכול להוציא את האלפות מהסכום, נכון?
לא, אתה יכול להוציא את האלפות מהממוצע ולא מהסכום.
מהממוצע, נכון, סליחה. זה I, זה J.
לא, זה ברחן.
זה בדיוק השונות שהייתה לנו? 2, T, טאו, דלתא, בלה בלה בלה. אז אתה רואה יוצא לי ש...
אתה שיקרת לי עכשיו.
מה? לא הבנתי.
לא, אוקיי.
מה מהדברים האלה שיוצא ש1 שווה 2? מה? שעבור K ואלים שונים יוצא שיש לי כאילו שונות משותפת עבור רכיבים שונים. קיצר, אני אראה לך את זה אחר כך שוב.
לא, זה דולק, אבל...
זה היה לכתום ועכשיו זה על ירוק.
ירוק זה טוב? Okay, Haran is here, Abraham is here, Jonathan, Gadi arrived in his house on his back, as usual. Okay, who else? Enrica, Tal, Jonathan, Ben, no, Daniel, no, Daniel. Okay, Rotem, Talia, Tamar, אמיר, אבל יש לך משקפיים פתאום. אוקיי. אמיר, אז לידו זה רועי או עמרי? רועי, יפה. אוקיי. Okay, very good. Today we will review the topic of the ring attractor. תודה. this is the, as we'll see during the discussion today and tomorrow, this is one of the most popular network model of spatial processing, by which I mean networks of neurons that represent the activity, represent space, either in the visual sense or in the sense of the space where the animal is, or in the sense of head direction, and etc. Representation of space, either one dimension. Most of what we'll talk will be indeed in one dimension, but in many important cases, the reality is at least two dimension, and therefore we'll talk later on a little bit about extensions to higher dimension, particularly to two dimension. But the principle actually can be well understood if we just limit ourselves to the simplest case, one dimension, and this is the origin of the name ring. Because if we are talking about coding of one dimension, it's a location in space, so it's basically points along a line. However, for simplicity, as we'll see later on, the reasons, we will take the line, the curve, not a straight line, but actually a ring. So we will assume that both the architecture has a ring structure, and also the stimulus or the external variable that the system is coding has an angular structure. Okay, so to be more specific, we are going to assume a set of neurons that are n neurons that each one of them has a preferred angle, which I'll denote by theta I. So I goes from 1 to n, and theta I is simply uniformly distributed. So it's minus pi plus 1 over a pi over 2n, etc. Up to pi, or up to pi minus pi over 2n. So basically we have, geometrically, we can put the neurons along a ring, not that they necessarily on the brain lie on a ring, but we can think about a functional architecture which has a ring structure, and by this I mean that each neuron I can represent by a node on a ring where the nodes are uniformly spaced, and they cover the range of angles from minus pi to pi. Okay. Now, what does it mean that I put the neurons along the ring? It means that first of all, that each neuron has a preferred angle, and this means that if I look at the input to the neurons, let me denote the external input. I'll denote by h I of theta. Theta is the angle of the external stimulus. And again, what is the external stimulus or what theta means really depends on the particular application. Whether it means a location of a target for a saccade along your ring, as in the Goldman-Rakish experiment, or the head direction or orientation in visual in V1, whatever it is, we will consider an angle as the parameterize the different stimuli. And HI is the input of a stimulus theta for neuron I, okay? And when we say that it is the neurons are characterized by preferred angles, first of all, it means that HI of theta has the structure of a function of theta minus theta I, and we assume it is symmetric function. So if I plot here theta, then we assume that there is some curve like that. This is theta I. What I'm plotting here is HI. I'm already abusing notations by writing HI of theta in one hand side and then using the same H to write the function of theta minus theta I. But
So about this notation means that the input of the HI is the input of the I neuron when the stimulus theta is presented equals to the total input, the other H is the total input.
H is the external input. I wrote external input.
Yeah, but HI is the external input of only one neuron, and H is the external input of the system.
I just don't understand what you're asking. I'm assuming that HI of theta is really a function only of the difference between theta and the preferred angle of the neuron theta I. What?
H is the same function for all neurons.
Which means that H is the same function, but just displaced. So this is if this is HI of theta, what I'm plotting here, then different neurons will have, let's say, this will be for neuron number for this will be H1, and the other neuron will have this, and this will be roughly. This will be for neuron number 2, the input, etc. So different neurons for so this is the stimulus theta, and this is how different neurons will respond to it. Another neuron will respond here, etc. So I mean that the external input, the profile is the same for all neurons, and it's only a function of theta minus theta I. Okay, this is the external input. Now we have also to talk about the interaction between neurons. So I'm going to assume that there are recurrent connections. And we call it W, I, J, the interaction between the presynaptic neuron J and postsynaptic neuron I is, again, some function W of theta I minus theta J. And again, we're going to assume that it is symmetric and has, like here, has a single peak. It's not complicated structure. So again, I'm going to draw now the function W as a function of theta I minus theta J. This is now the function W, and it will have some profile which has a positive is positive near the origin and negative for far away. So a kind of Mexican head structure, which means that neurons which are close by on the ring, so this is W, this is I, this is J. So neurons which are nearby on the ring are exciting each other, and neurons which are far away are inhibiting each other. So essentially, these are the main ingredients. Okay, if you can see from here, the entire thing has a symmetry of shifting. I can shift all the angles by some arbitrary constant number, then the interactions won't matter because the distance between them is the same, and the only thing which will matter is that whatever the external input was, I have to shift it by the corresponding angle, and then everything will remain the same. Okay, so that's what I mean by ring architecture. So don't think about rings in your brain. Think about interactions of functional architecture which has this structure. Yes?
If it's on the Mexican head, the neuron that is just opposite from the neuron we're looking at,
That's what?
the neuron that is just opposite.
I don't really talk about just opposite. This is a general, whether it's just opposite or not. It's details which we can discuss. It doesn't really matter whether just opposite or not. The general thing matters is sort of the qualitative structure. Nearby neurons excite each other. Far away neurons
Why
inhibit.
does it slope up?
It doesn't have to. It doesn't have to. It doesn't have to. What?
It doesn't have any effect on very far away neurons.
That's not the way I drew it. It is so, but I said it's not essential. I repeat, what is essential? Nearby excitation, distant inhibition. That's what's essential. Whether it falls away and how it falls, or whether it remains negative or not, these are details, and we can argue about it later on. Okay. Good. Now, finally, I'll write down the equations, the dynamics. I'll assume rate dynamics. This will be tau dri dt equals to, let me just, I'm sorry, before that, add here 1 over n for normalization, as we discussed last week. So then now there will be here, plus some nonlinear function of the total input, which I'll write as I of t, kind of the current, the total current. I just don't want to introduce upper indices here and so on. So H will be the external input, and I will be the total input. And I of t is, first of all, hi of t. In principle, it could be a function of time. So let me write it hi of t, which has, again, this structure. It will be function of time if for some reason the amplitude changes the time. Let me assume this structure, so it will be simple. Hi of theta, without making it overly complicated. So h of theta I minus theta plus 1 over n times sum over j of w theta I minus theta j times rj. Okay, and f is some sort of nonlinear function, as we discussed earlier. All right, so we have recurrent connections, we have the external inputs, the general structure, and the dynamics. So let me then take a concrete example, which will help us to analyze what the system is doing. Before that, what I'm aiming at is to address the question, what what happens to the network when the spatial modulation of the interaction is strong. So we discussed last week the simple case where neurons just have a uniform recurrent connections, excitatory or inhibitory. So this is kind of simplest non-uniform case. And what I want to address the question not when, what happens when you increase excitation or what happens when you make the inhibition strong, but what happens when you make the spatial modulation strong. Imagine that you keep the mean interaction the same, but you make it modulated, strongly modulated. What happens? Does anything qualitatively happens to the network?
We're going to have now W connection matrix will change to develop in time.
Well, W doesn't develop in time.
No?
No. More questions. Okay. So that's so this is the overall goal, and I can tell you already the answer to that question. The answer is that when the modulation, the spatial modulation of the interaction is strong. What?
What do you mean by strong?
We'll talk about what I mean by strong, but when it's strong enough, okay, then the network will tend to develop on its own spatial structure in the activity pattern. Namely, even if the input is uniform, even if the input doesn't look like that, but simply uniform input to the network will not like to stay in a uniform state. The homogeneous state or the uniform state under those conditions will be unstable. But the consequence of this instability will not be simply epileptic network, but will be a network which develops a spatial structure. Spatial structure, I mean that some neurons will be active more than others, some neurons will be inhibited. There will be a spatial structure which is formed by the recurrent dynamics, even in the absence of any spatially modulated external input. Okay? So how do we get to it? How do we analyze it? There's extensive literature, the original papers and review articles and so on. Some of it we'll put in the website. But I want to give you some flavor of such an analysis. And I won't go into all the details, but I'll give you the highlights of the analysis. How do we analyze such a network? Okay, we have n equations. We have non-trivial interactions, non-trivial external input. How do we make progress aside from just putting it into computers and simulate it? So the first thing which I want to do is to simplify the general structure, namely take a specific example, a specific case of H and a specific case of W. Again, this just an example to teach us the general rule, but it's a useful example. Okay, so what I'm going to say the following. In general, H of theta, right, because it's a periodic function of theta, right, everything is, theta goes from minus pi to pi. When you go from 0 in H to 2 pi, everything should be the same. So therefore, this in general has the structure of a Fourier series from n0 from, I don't know, let's say from 0 to infinity of hn times cosine n theta. The reason why I'm writing only cosine because I'm assuming it has this nice symmetric structure around the peak, so the phases of 0. Okay, so that's a general way to parameterize a function like that. And similarly, W of theta I can write as similarly as sum n goes from 0 to infinity of the Fourier coefficient Wn times cosine n theta. Okay, so that's the general structure. That's again not simple enough, But now I'm going to make the further assumption that I truncate those series beyond the two terms, the two first terms. Okay? So truncation will be, I'm going to assume that h of theta has the structure of h0 plus h1 cosine theta, and that's it. And I throw away higher harmonic. So now h will not really look like that, will look like a cosine. This is more like kind of a Gaussian. Okay? So that's our model for h, and similarly our model for the recurrent interaction profile will be W0 plus W1 times cosine theta. Okay? So again, in this case, the interaction profile really doesn't look like that, it will look like a cosine. Okay, so, it will be something like something like that, a cosine. There is a, okay, if I just make the plot not so cluttered, then W will look like that, and what W0, I shifted it, up and down. In this case, it was down, so you can think about the mean of that. In this case, maybe it is this. The mean of this will be W0, and the modulation, the amplitude of the modulation, the difference between the top and the bottom, the maximum and the minimum, will be 2W1, right? If I look at the distance between this, the minimum and the maximum, it will be 2W1. W1 plus W1 up to minus W1. Okay, so that's what I mean, the modulation. W0 is the overall mean recurrent interactions, and W1 in this case tells us about the strength of the modulation. If I put W1 to 0, I'll go back to uniform interactions. If W1 is strong, means that the interactions are strongly modulated in space. And similarly for H. Okay. Okay, so this is our model. One more thing which I would like to add is, since in many cases we're talking about cortex, and we're talking about input to cortex from other areas, or from LGN, from thalamus, then in most cases those external inputs are excitatory, and therefore we're going to assume that H1 is bigger than 0, but less than H0. And that's kind of the range of the parameters of the external input. Again, that's not crucial. We can, of course, one can extend it to cases where the input is inhibitory, has also inhibitory component, but that's fine. So in this case, the input will be excitatory but modulated. The interactions in general will have excitatory part, inhibitory part. It all depends on this coefficient W0 and W1. All right. So the next step for studying the network is taking the large N limit. is assuming that there are many neurons. Now, it's not enough when you have non-trivial structure for the interactions. It's not enough just to say, well, we assume that there are many neurons, that n goes to infinity. It's not even, you know, we had this. You have to say something about not only the strength of the interactions, as in the all-to-all network that we discussed last week, but also in the range of the interaction or in the width of these curves. So in particular, what we really want to consider the case where there are many neurons, I don't know, thousands or millions of neurons, depending on what system. But furthermore, each neuron receives many inputs. And each external input activates many neurons in the network. Okay? And essentially, the way we formalize it, we say we want the external input to activate a fraction of the neuron in the network. Okay, let's say the fraction will be, the width will be 20 degrees or something like that, or 45 degrees. And similarly, the interaction, each neuron will get a fraction of neurons as presynaptic sources to it. This actually means that as we take n, if we think about n becoming larger and larger, the width of those curves remain finite in terms of angles. Okay? So basically, as we wrote here, basically W0 and W1, in this case, I'm sorry, W1 and W0 simply will just scale with n. In other words, W will be 1 over n times this, and this is fulfilled now by this form. So what I mean is that as n becomes large, nothing happens to these parameters, h0 and h1. They remain constant, and they ensure that the profile in angle remains constant. So we don't want to consider a case where a neuron receives input only from its neighboring neurons, 2 neighboring neurons, or 3 neighboring neurons. That's not the case we want to consider. Or consider where the input just activates only 2 neurons. Okay, so these coefficients are going to remain fixed as n goes to infinity. So that's also is sometimes called the continuum limit. Because under these conditions, we can assume that the network profile, you know, now we're talking about the profile of activity of the neurons. Well, it depends on age, on these parameters, on the parameters of interaction, but in general, it will be a profile which is characterized by the angles, right? When not by, you know, a neuron, two nearby neurons will share the same activity or be very similar activity. So in this case, R I of theta and T, the activity of the neuron I with external input theta, and time T, I just write it as A of theta minus theta I and T. So there will be some angular profile A. So I'm running too fast. This is no. Let me use different notation. Sorry. Let me just use this notation. Ri of theta. I'm sorry. Ri of t, as we had in some equations. I'm going to write it as A of theta I and t. And theta I is going to be now continuous variable. Okay, so in order not to confuse, or maybe already confused you, but maybe not, let me go back in your notes. Let me add theta 0 for the external angle, and put here theta 0, and put here theta 0, just to make sure that we understand each other. So this will be theta 0 here. And I'm going to write this as simply A of theta and t, by which I mean, if I look at the network, so this is now theta, not theta 0. This is the coordinate, the columnar coordinate, let's say in visual cortex, and I have, I don't know, some profile. So this is now going to be A of theta and t, at any given time, the profile of firing rate along the coordinate theta. So let me write here theta 0 and theta 0. So now we make sure we understand what is the external variable and what is the internal variable. Question? Well, no, theta is just theta I. I don't. I mean, there is no reason to keep the index I. Not theta I. W is a function of theta I minus theta j. So this is just W is a function of the angle. So this angle is theta I minus theta j. This is the external angle. And this is just theta I. I mean, I can keep on putting i's, but I and I and j, but there is nothing to be added to this. I mean, I is from 1 to million, but what's really important is what is the angular variable of this neuron. If this neuron is in an orientation column with horizontal, then theta is 0. If it is vertical, theta is pi over 2, or in head direction, similarly, and so on. So I index the neuron simply by the angle. What? So let's see. So instead of writing, so you'll see what I do. So instead of writing, where is it? So instead of writing this equation here, I'm writing it tau, essentially partial differential equation, tau dA. So now the activity profile is a function of two variables, time and space. So now t equals to minus a of theta and t plus f of I of theta and t, and I of theta and t is h of theta minus theta 0 plus, so now instead of summing, so we had 1 over n times sum over j here. This one turns into an integral. Integral d theta prime from minus pi to pi, normalized by 2 pi, of w theta minus theta prime times a of theta prime and t. So that's what I mean by continuum limit. Everything becomes space, or spatial summations becomes integral. So technically is differential integral equations, because there is a differential in time and integral in space. Furthermore, I can now put this ansatz into, right? So I can write this as I is H0 plus H1 cosine theta minus theta 0. I'm sorry. Yeah. Sorry. if you ask me, then you should have asked me. This is h of theta minus theta. What happens to Ran? He's too quiet. I don't like it. H should be a function of theta minus theta 0. Right?
I'm giving them the chance.
What?
I'm giving them the chance.
Come on.
What does it matter?
Sorry. This is h of theta. H I of theta 0 is h of theta 0 minus theta I, and therefore it is this one. So, okay, so h0 plus h1 cosine theta minus theta 0 plus what we have here. We have w0 times the sum, the integral of a. Okay, so the integral of a I'll call a0. That's the mean of a, I'll define it soon. Plus w1 times cosine times the integral of a. Right? Let me write it explicitly. Here I'll have d theta prime over 2 pi of a of theta prime and t. And then the second term will be plus w1 integral d theta prime over 2 pi of cosine theta minus theta prime times a of theta prime and t. All right, this is simple. This is just the average of a. Mean activity, this is simple. This is kind of, we have to unpack this, so let me unpack it a little bit. The reason why it's kind of ugly is because there is a of theta prime, but here there is cosine of theta minus theta prime. So let me write it in the following way. Let me introduce what's called order parameters. Oh, not here. Let's do it here. I'll say a few words about the name, but let me just define them for us. All the parameters will be A0 of t is simply the mean, spatial mean of the neuronal activity. That's A0, so that's what appears here. Here I'm going to introduce the following integral, d theta over 2 pi of a of theta in t times e to the minus I of theta. Minus a plus, let me see what I use. Minus, okay. All right. Why do I do this? Why? Because you see, the way to deal with this is to expand this into cosine, cosine, and sine, sine, using the trigonometric relation, and then relate this to the Fourier transform of A. But there will be contributions from the cosine, contribution from the sine, which means that in terms of complex Fourier transform, there will be a phase. So this is why I write it like this, because this gives me, it's a complex quantity which gives me the cosine Fourier transform and the sine Fourier transform. The real part will be cosine, the imaginary part will be minus the sine. And we need both of them because we have here this cosine of theta minus theta prime. We have both. Okay. What? What again? What is the question? No, not at all. Not at all. I'm going to write this. I'm playing the drama. I want to. So this is a complex. This is a complex Fourier transform of A. right, with the Fourier number 1, right? Since it's complex in general, there is the real part, imaginary part. Or conversely, I can write it as the amplitude of this and the phase. So I'm going to write this as A1 of t e to the minus I psi of t, not psi of t. Okay? What? Psi, not psi. Psi. All right. So one way to think about so this is just the definition. This is the complex number. A1 is by definition a real number. That's what I define A1 to be the amplitude of this, and psi is the phase of this complex number. That's the definition. Another way of defining it is by removing the psi here and writing this as A1 of t equals to d theta over 2 pi. Whenever I don't write the boundaries, it's from minus pi to pi, of A of theta and t times e to the minus I, and here I open a parenthesis, psi minus theta minus psi of t. I simply brought this phase and multiplied it here on the second side. And now I can write down what is A1 and what is psi of t. Why I can write it? Because A1 has to be real by definition. So then A1 is just the cosine, right? So I can write A1 of t to be d theta over 2 pi of A of theta and t times cosine of theta minus psi of t. Because A is real, then it's identical to the cosine. And the imaginary part then has to be 0, because this equation is real, and therefore the imaginary part is 0. So 0 equals to d theta over 2 pi of A of theta and t times sine of theta minus psi of t. So let's look at these two equations and let's say a few words about the meaning of these two equations. So what do I have in mind? I have in mind some input, which is kind of modulate the network, and then there is recurrent interaction, which adds to it, and then there is some activity. Let's say some bump of activity, which I call A, at some time. So this is theta again, and this is A of theta and t. This is a function of theta at a given time. Let's say the profile looks like that. So what is psi, first of all? Psi says take the profile and integrate it with the sinus of angle. You should get 0. Well, so this means that psi of t is basically the peak or the center of mass of this profile. Because if profile looks like that, and if I integrate sine times this, I'll get 0, because this is kind of nice symmetric, and sine is odd function.
It doesn't have to be symmetric.
Well, it doesn't have to be symmetric, then psi will not be the peak, will be slightly different from the peak. Psi is the phase of the entire profile. Psi characterizes the phase of the entire profile. How do I define the phase of the entire profile? What I want to say is, suppose I take this profile and shift it a little bit without changing its shape. Then the only thing which changes is not A1 and not A0, but psi changes. The center will move. Now, it's not going to be necessarily the peak, depending if it's symmetric. If it's not symmetric, it will be something else nearby the peak.
I'm not sure I understand. Do you mind
Okay.
maybe drawing two
This is the definition of psi. I have to look. I have a profile. This is theta. This is, I don't know, this is minus pi here, and this is pi here. Okay? I want psi tells me where the profile centered. Okay? If I shift the profile, it's simply shifting psi. So how I define kind of the center of the profile? I say pick an angle such that relative to this angle, the integral of a times sine will be 0. The simplest case, think about a profile that has a symmetric form around some value. Okay? So if you define psi to be at the peak of that symmetric form, you multiply it by sine, which is an odd function. This is an even function. This is an odd function. You get 0. So that's a definition of psi. Look for an angle, given the profile, look for an angle that represents where the profile is located. Okay? Find psi in such a way that the integral of that should be 0. If it's not symmetric, then psi will not be at the peak, will be slightly different from the peak, but it doesn't matter. It will be the same. The important thing is that psi is such that if you shift the profile without changing the shape, simply you shift psi. A1 then is simply relative to this peak, the cosine Fourier transform of A. Very simple. The first Fourier transform relative to this center. And A0 is simply the mean activity. So when I take a profile of activity and shift it, the only thing which changes is psi, not A0, no A1. A0 is the mean finding rate. A1 tells me the first Fourier component of the modulation of the finding rate, of the pattern. Psi is telling me where the pattern is located. Okay? If I change the location, if I change psi, I change the location without changing anything else. So you can imagine, in particular, think about the external input, theta 0, as some, moving. Suppose I'm on a chair and I get a vestibular input and kind of moving in a circular way, then simply psi will move in some way, but the shape of activity, if it's kind of slow enough, will remain the same. It's only shifted. We'll talk about dynamics later on, but that's the idea. So we have 3 order parameters, 3 parameters which characterize the profile of activity: the mean, the spatial modulation, and the phase, the location of the population of the pattern of activity. Okay? I know. I listened. I didn't obey. Okay. Okay. הפסקה.
גל, זה הדבר הזה. אני חושב
לא,
ש-
אתה יכול, אתה יכול מבוססת.
לא, אם זה דרך מדריך ביום כזה.
כאילו, שמתי שעון, זה לא יודע, עכשיו לא לחצתי פליי על התוכן.
זה שווה מספיק. מה זה
זה
מספיק?
וקטור, שווה למטריצת U, מטריצת הוקטור האורתוגונלי של W.
זה לא מפריץ את מעבר בתי.
אתה יודע שהיום הנוף ניגוד.
כמה אתה מבוסס את זה?
לא, אבל אני קוראת את זה לפי הלקטור מהחיים של ואלי, אני לא...
זה עדיין מעבר בתי. אוקיי, בסדר.
אני רק קוראת את
זה
זה
מעבר.
פשוט הזה.
אוקיי.
ואז קפצתי ביולי לפחות לפני הסיפור.
אוקיי.
זה אתה מסכים? אז עכשיו בוא נשאר לך, זה גל, כול זה גל חד. בסדר? שזה ליו מינוס אחד, נט, כפול יו מינוס אחד, זה זמן פותחת את הסוד.
אתה רוצה שזה תהיה מטריצה, אז זה מטריצה קומרית.
זה מה ששווה יו מינוס אחד. זה טרנספוז, יו מינוס אחד טרנספוז, אלה. נותנים לי מטריצת יחידה.
עכשיו, יהיו אורתוגונלי, נכון?
אתה יכול אפילו לומר את זה
יהיו
שיהיה
אורתוגונלי, נכון?
נורמלי.
אז על אחת כמה וכמה, אם את טרנספוז האלה הולכים,
אז זה.
ואז כל הדבר הזה זה קבוע כפול מטריצת יחידה, אז כל הדבר הזה זה מטריצת יחידה, אז זה יוצא שהם עדיין כאילו...
רגע.
אז בקטע, לא הייתי לדעתי כמה זה מעבר בסיס בין עדיין בלתי מתואמים.
יו מינוס אחד טרנספוז, זה אומר למה?
מטריצה אורתוגונלית זה טרנספוז של ההופכי של הזוגות.
שאלה ראשונה,
הטרנספוז ההופכי זה מטריצה של הרגיל. כל הדבר הזה יוצא...
בדיוק, אתה לא יודע מה קרה לי. השארתם את האוכל בבית. גדי, אני חשבתי על זה שהיום אתה תמיד אוכל, ואמרתי, אוקיי, גם אני אוכל אוכל, כדי שנוכל לאכול ביחד. באמת שעה כאלה להתאבד. מה כבר נשאר בן אדם?
מטריצה אורתוגונלית זה טרנספוז של ההופכי שלה זה אותו הדבר, נכון?
מטריצה?
נגיד מטריצה שהעמודות שלה הם וקטורים מעצמיים של W, אז הטרנספוז של ההופכי שלה זה אותו אחד, נכון? לא?
כן.
היא אורתוגונלית.
כן, המטריצה זה כפול הטרנספוז שווה להם אחד, כן.
כן, סבבה. זה כאילו, אבל זה מטריצה אורתוגונלית, זה מטריצה שכאילו העמודות שפורצות אותה הם כולם מתאבות
כן, ואז כאילו מה שמפתיע זה שאם אתה תיקח 5 וקטורים אורתוגונליים תסתכל אותם בשורות, אז העמודות שיווצרו לך יהיו גם אורתוגונליים. זה סופר לא...
בתרגיל זה גם יצא לא אינטואיטיבי לדעתי, כאילו על השאלה שהרעש לא מתואם גם בבסיס השני, כאילו.
למה? תחשוב, אתה לוקח סט של uncorrelated גאוסיאן עם אותה שונות, כל טירוף לינארי, גם uncorrelated גאוסיאן.
We just want to mean.
כל טירוף נראה לי כאילו אתה פורץ איתו בסיס.
כי
חייבים להיות...
ראינו את זה, כי פשוט המטריצה, טירוף לינארי שלהם הוא גם גאוסי, מטריצת קורלציה שהיא המטריצת טרנספורמציה, כפול המטריצת קורלציה המקורית,
אתה אומר להתפלגות של כל אחד היא אותה התפלגות בדיוק, זה אותה התפלגות גם לתחום שלך.
Anyway, how's it going?
גם לא כזה.
You guys working today?
אם ממש תכתוב את זה לפרטים זה יהפוך לאינטואיטיבי, אבל ככה, זה לא מה שחשבתי שיקרה, חשבתי שבגלל שפרקנו אותם הם יהיו מתואמים, בגלל שכל אחד מהם תלוי באותו נוירון.
כן, והקטע המפתיע הוא שמה שיקבע אם הם יהיו מתואמים אחרי אם עושים להם צירופים לינאריים או לא, זה לא אם הם לא היו מתואמים בבסיס המקורי, אלא אם השונות שלהם הייתה שווה בבסיס המקורי. אם זה היה מלוחצן, נניח יש בסביבות כן לא מתואמים באיזשהו בסיס, אבל עם שונויות שונות...
רק בגלל שזה משהו שאנחנו מטריץ את יחידה.
כן, שזה בכלל,
טוב, זה... צריך לשנות משהו בכל המטריץ. ואני שכל ההמשך היה נכון. חוץ מזה, טיפים בדבקים בנאים יכולים, וחשבתי מה אני אני חושב שבאוזן אחד שאני יכול לדבר על זה משהו שהוא באוזן בנתיבות שלך. אתה שאני איתך על זה. אבל כל המשך היה סבבה. מחר, נכון. אני רוצה לסיים את חישוביות, אבל
integration under integration.
רגע, אבל אני לא בסרט. איך זה אינטגרל שם? אני לא בטוח מה זה. כן, אחד שם בתור E ו-C
F של E, F של Z.
אבל זה גם אחד גם של H
אבל פה אין לך F של A. לא סתם. זה עבר על זה בכלל.
ועוד אחד שינוי גרפון.
זה עבר על זה, זה F של A.
יש עוד אחד
E by X ו-Z by.
ניטרלי.
אבל פה אני צריכה לגזור
אבל F של A זה לא מופיע.
אבל
יש פה אינטגרל של משהו שלא תלוי ב-H. E שמופיע כשאת משנה את H, מה משתנה?
כן, זה גם
כמה זה מסתירה.
זה שיובל זה אינטגרל,
F
בא למעסיקים בשלטון לשם
רגע, יובל הוא למד רפואה? איך זה משתנה? איך הכמות הזאת משתנה? מה שיש פה באינטגרל? כמה שתשמע.
So you're not using it over.
לא, היא, סליחה.
Okay. Okay, so we looked at the total input to the neuron theta, and we had the external input, constant plus cosine theta minus theta 0, and then there is a recurrent which we wrote in terms of, or we are going to write in terms of the other parameters which I just defined, and and I leave the details to you. It's very simple geometry. This is that I can now write I of theta and t. I'm looking now at this equation and write it as h0 plus h1 cosine theta minus theta 0 plus w1 times a0 plus w0 times a0 plus w1 and sorry, plus without the integral, plus w1 times a1 of t times cosine of theta minus psi of t. So there is an integral here, but the integral is simply the Fourier transform of A, and there is a phase enters here, and the phase is given by minus phi of t. So if you put this definition of psi and A and put it back here, you can do the integral. You can actually perform this integral explicitly and write everything in terms of this. So that's kind of interesting, because what does it mean? It means that we have now, let's write the equations. We have now tau dA theta dt. I'm rewriting it, minus A of theta and t plus some nonlinear function f of I of theta and t. And I is now given in the, I is given in the equation above. Okay. Now, why this is important? Because the unknown is a profile, right? We have to find out how A looks. You know, what is the spatial profile as the solution of this equation for given external input and parameters of the interaction. But the right-hand side is not a function of the entire profile. It's a function only of three parameters characterizing this profile: A0, A1, and psi. That's only parameters which enter into the right-hand side of the equation. What about what? Well, f is not unknown. F is whatever our sigmoidal function is. Which means that instead of working hard to solve self-consistently for the entire function a of theta, I just have to find the solution for a0, a1, and psi. And how do I do this? I simply take this equation and collapse it. How do I collapse it? I integrate over theta, and then I get tau dA0 dt equals to minus a0 plus the integral of this, f of I of theta and t. It's one equation. And then I have equation tau dA1 dt equals to minus a1 plus d theta over 2 pi of cosine of theta times f of I of theta and t, cosine of cosine of theta minus psi, as before. And then 0 equals to d theta over 2 pi of f of sine of theta minus psi of t times f of I theta and t. So basically, I have three nonlinear equations for three unknowns, a0, a1, and psi. And the right-hand side is also a function only of these unknowns, a0, a1, and psi. So instead of solving for the entire network, I just have to solve for these three unknowns.
In the equation for A0,
Yeah.
not to plug in the I also with only the A.
But I has a0, a1, and psi in it. Doesn't have the full a. I is a function, is cosine. There's some well, I'm not saying, still one has to, I'm not saying that the solution is necessarily easy, but we have here nonlinear equations for three unknowns rather than nonlinear equation for the entire profile, which is a function of theta. There is no a of theta anymore in these equations. It's a0, a1, and psi.
Why do you plug in the cosine?
Because that's the definition of a1. So you take this equation, you multiply by this cosine, and you integrate, you get this equation. And similarly for this. Now, before I answer, I want to emphasize, I do not imply that a of theta and t has only, the first, the 0 and the first cosine component. I do not imply that the profile A, when we solve it, would just look like cosine modulation. That's not true in general, because there is nonlinearity f here. So if I take some cosine inside and apply the nonlinearity, I'll get something which has all the higher harmonics. F, modifies the function and can turn, in general, will have many harmonics, okay? Only in the linear case, this will have only cosine. In the nonlinear case, A can be something like this, can be, shaped like this. Narrowly tuning profile, this is theta. Okay? In this case, you have all harmonics in it. What I am saying is that in order to find A of theta, in order to find the profile, I just have to solve self-consistently for A0, A1, and psi. Once I know them, I am done, because I know what I is, and then I can just plug it here and solve. There was a question here. Omri. Yeah. Okay, go ahead.
Zero of the third equation.
Yeah.
Because A is symmetric around psi,
There was?
the reason there's a zero on the left side.
Because if I put here, I multiply by sinus, okay, and I put it here. Now this says that A times sine has to be 0. All right, so actually you're right. I mean, you know what? Actually, if I let's do it, right? If I multiply this by sine. No, actually there is a term here. It's not 0. You're right. You know, this term will be 0. This term will be this, but here you're right. It's not 0. It is. I should multiply. What do I have? I have d dt. I have a dot times sine, right? If I multiply this by sine, I have a dot times sine. Okay. So if I want to take it out, you're right. There is two terms here, right? There is a term which is the derivative of everything, which is 0 because everything is 0. But there will be a term which is derivative of this. That's very interesting. Okay, exercise, homework. What should be here? You're right. It's not 0. It is. Okay, I'll tell you what it is, but you have to prove it. Okay? So that's interesting. I take this, the entire equation, and multiply by sine and integrate over theta. Okay? So this one is 0 because a times sine is 0 according to this equation. This one is what this one is. But now I have the left-hand side, I have this one. Now, a dot I can write as the derivative, the full derivative. The full derivative must be 0 because this quantity is 0. But then I have minus the derivative of this, which is minus minus, so it will be plus. So it will be cosine times sine dot. So this will be a1 t times psi dot. Very good. Omri, very good. מה השאלה? נכון, זה קוסינוס, וקוסינוס זה A1. אבל יש לי גם את הנגזרת של פסאי שמופיעה כאן. לא, אבל הנגזרת המלאה פחות הנגזרת של זה. לכן יש לי פחות, לכן זה פלוס. מה? טאו. Okay, that's right. תודה עומרי. That is the third equation. It is, you know, here I should not write partial differential equation because these are numbers. These are scalars, are not functions. Are just function of time. So now this one will be d psi dt. Very good. 1, 2, 3. Okay. So the bottom line is now very simple. Take whatever h0 is, whatever h1 is, whatever theta 0 is you know, the parameters of the external input, the W0 and W1 parameters of the interactions. You have some initial condition for this A0, A1, and psi. You just plug it into, you just solve these equations. From these equations, you get A0 is a function of time, A1 is a function of time, and psi is a function of time. Once you have this, you can go back here, plug it into I, and just integrate this equation. You don't have to solve anymore because this, you know already what I is. Very simple. Talia is impressed by the simplicity. Oh, but my definition of simplicity. Okay, very good. Now that's cool. Okay, this is why I call this order parameters. When the order parameters are the parameters that characterize the collective property of the activity profile of the network, which determines the fate of the dynamics. In other words, the profile is slave to this A0, A1, and psi of t. Okay, once these are given, nothing else can happen except for us integrating this equation, but there is no drama will further emerge. The crucial thing is to understand what is A0, A1, and psi. And these are all the parameters. They're collective. They're not activity of a single neuron. They're characterizing the shape or the magnitude of the activity of the entire network. The mean, the modulation, the location, and so on. Once I know them, I know the rest.
So A1 is like how much difference there is between the excitatory and the inhibitory neurons?
No. Okay, not excitatory inhibitory neurons. These are not the wrong terminology. Wait, the wrong terminology, because neurons here I didn't separate into excitatory inhibitory neurons. I talked about W, has excitatory part and inhibitory part, but these neurons are not. I didn't talk about neurons which are excitatory neurons and inhibitory. What? A1 is A1 is suppose I have some profile of activity, something like that. Okay, so A1, A0 is the mean activity, mean over the network. A1 is the modulation. How different is the maximum for the minimum, for instance? The magnitude of the modulation. If all the neurons have the same pattern of activity, then integral over cosine is 0, then A1 is 0. If A is constant in space, then A1 is 0. So A1 captures the modulation, the spatial modulation. Psi, the location. Psi says, okay, you have a modulation, but is it here or here? That's psi. Okay. Ken.
The activity will be always localized also because we have psi will be localized with one peak. Like it will be, it won't look like a psi model.
Well, no, that depends on the details. Imagine that I started the network with some crazy initial conditions where 2 columns are active. This is my initial condition. So even if at the end it will be nicely like this, it will start with this and then converge to this. Okay? But still, psi is well defined. You just take this, find the phase. Maybe it will be, if it was something like this, psi will be here. Psi is the position. There is always a position. You can prove that whatever the profile is, there is always a position, a center around which the sign will be 0. That's always the case.
That's simply the center that makes the...
Yeah, but whether the center or if the profile is crazy, it will be slightly shift to the center.
Yeah, but it makes the area of this function equal in both sides. That's the definition, right?
More or less, because you multiply it by sign, it has to be 0. So more or less, it's the position where if you multiply one side by sign, you get a positive quantity. If you multiply the other side by sign, you should get negative quantity, and they cancel each other. So it's a kind of the center.
So it's the center of the edge.
Yeah, roughly. Okay. And also, and again, I want to emphasize what the actual, position of psi. What's important is once you have psi, whether it moves or how psi is related to the external input, theta 0, and so on. And we will see examples of that. Okay, so from now on, just examples. Examples how the solution look like. So let me... Okay, so now concrete conc. Okay. First of all, I'm going to assume f of x to be threshold linear. We also write it as x, x minus some threshold t plus. The parenthesis plus means that it is 0 if the argument is negative, and otherwise it is the argument itself. So f of x looks like that. If this is x, and this is f, if x is below threshold, it is 0. If it's above threshold, it's just x minus t. So that's the simplest nonlinearity, and turns out that many of the properties of nonlinear networks, at least at the rate dynamics level, are captured by this nonlinearity. Yes?
Sorry, I'm a bit confused about the third equation. You had the time derivative of A, right? And then you multiply both sides by the sign and do an integral.
The third equation?
Yeah.
Homework. Homework. I mean, it doesn't, I mean, okay, so it's different equations still, what I said is right, so don't worry. Homework. All right. So let's go back. This is my assumption for f. Simply it's threshold linear. So, okay, one assumption. Second assumption, that we are going to look at the stationary state, which means I'm going to look at the static condition. I'm going to say, let's assume there was some initial condition. I don't care. I just look at the stationary, the fixed point. Talia, at the fixed point of the network. Okay. So that's assumption number one. So I'm going to assume that A dot is 0, etc. So putting to 0 the left-hand side of these equations. Okay. And now I'm going to do first part, 2A, is the linear regime. What does it mean? I'm going to assume that I is such that it's always bigger than threshold. So, and then, in other words, H0 and H1 and so on are such that everything, all the neurons are above threshold. That's a very simple case. Then the whole thing is linear. The f is just I. F is just I. F is just I. Very simple. All right. So in this case, it's very simple equation. Imagine you take I here, and you put back f. You put back this, and you integrate over theta. Then all the cosines drop because the integral of them is 0. Then we just get A0 equals to constant terms. So we get A0 equal to W0 A0 plus H0. So basically A0 equals to H0 minus T minus threshold, H0 minus T divided by 1 minus W0. That's the first equation. The second equation is A1. Again, I put F, so I integrate cosine. So now things are slightly tricky because H0 times cosine is 0, integral, and all the zeros components vanish, but what about the cosine component? Well, I have cosine theta minus psi times cosine theta minus theta 0. Okay? So it's going to be a little bit ugly, but I'm going to assume that the pattern A of theta in the stationary state, because there is no nonlinearity, then it will look like a cosine modulation, and it will be centered around theta 0. So psi equal to theta 0. That makes sense. Theta 0 is the location where the input is maximal, And therefore, it makes sense that this will be the location where the activity of the neurons will be maximal. And one can show that this is a solution, but it's the only solution for the linear case. So with this assumption, psi equals theta 0, I can compute A1, okay, because I have here A1, I put it here, H0 is 0, H1 times cosine square is 1/2. So basically I have H1 plus A1 W1 times 1/2. So you get A1 equals to H1 divided by 1/2, 1 minus, so 2 minus W1. And now this equation, at least you should see that it's self-consistently, because this is 0, the stationary state. If I take psi to be theta 0, then sine over everything will be 0. So it is self-consistent, right? Because sine of theta minus theta 0 times cosine is 0, times cosine this of 0, so everything is 0. So these are the three equations. One equation is this, and two equations is this, and three equation is this. Okay, so again, theta equal to theta 0 means that the external input locks the pattern of activity to peak where the external input is maximal. A very simple notion of how input determines the shape of activity of the network to the spatial pattern of the input itself. If the input is maximal here, then the activity profile will also be maximal here. Okay, this tells us about the mean activity of the network, mean response of the network to the mean activity of the external input. And this is basically the thing which we discussed last week about the amplification versus suppression. If W0 is excitatory, then A0 will be amplifying the input. If W0 is negative, A0 will be suppressed compared to H0 minus threshold. And this is something new. This is not something new, but in terms of eigenvalues, this is W0 is one eigenvalue of the interaction matrix Wij, and W1 over 2 is another eigenvalue of the interaction matrix. And now we see that this equation, again, is an equation that tells us whether the spatial modulation of the input is suppressed or amplified at the level of the output of the cortex. And that is determined by W1. W1 strong, A1 is large, W1 negative, then A1 is suppressed compared to H1. Okay? And now, with this, we can move quickly to the question of what are the instabilities or potential instabilities in this network. So there are two potential instabilities. One is W0 being above 1. Okay? As W0 becomes 1, A0 diverges. In other words, if there is too much excitation, things blow up. And when W0 is above 1, the linear system becomes unstable. But the way it becomes unstable, simply the entire profile of activity is rising, right? Because A0, that's the mean activity, is increasing, and the network is getting outside the linear regime. Okay, so this is what we call amplitude instability. If the network was strictly linear, then we just say that W0 cannot be bigger than 1 because the system is truly unstable, diverging. But since the network, well, in this case, actually, it doesn't, the network will diverge because this is, the nonlinearity is threshold linear. I didn't put any bound on the level of activity, so this will just explode. So it's not interesting. We're not interested in this. But interesting case will be W0 less than 1, but W1 bigger than 2. Then we have a non-trivial instability. We have an instability of the modulation, which means that if we make W1 closer and closer to 2, then the profile of activity will become, will still be cosine, but it will be stronger. The modulation will be stronger, stronger and stronger modulation. A1 will increase. And when W1 approaches 2, A1 diverges. So this is not, there is no change in the mean activity, but the instability is that the network wants to develop a stronger and stronger spatial modulation. And this kind of instability we call pattern formation or symmetry breaking instability. Now, this instability, unlike this instability will be stabilized by the nonlinearity of the network. Why is this so? Because as the amplitude grows, part of it wants to be very large, positive, but part of it wants to go negative. But F doesn't allow negative because it cuts the activity below 0. So that is enough to stabilize the network. But once W1 is above 2, we have to go back to the nonlinear. We cannot assume that the system is a linear regime because the nonlinearity, the threshold nonlinearity, it plays an important role. It stabilizes the dynamics. By making part of the network being sub-threshold and not active, the entire network is stabilized. Yes? Yeah.
So then we can know that A0 is strictly negative, and that's why you're saying that the system will diverge?
No, yeah, you can do it, but also we know from our stability analysis that I discussed last week or so that when eigenvalue is above 1, then the dynamics diverges as unstable. That's an example of that.
So can you repeat how the system will stabilize in the second case? You said the first case, the nonlinearity of F will stabilize it because it doesn't allow
The second stage, what do you mean by second? This one and this one?
when the second is
This one, we're not interested in this regime. We're not interested in this instability. We will assume W0 is less than 1. This instability doesn't really help us. I mean, the system diverges, so we just assume we'll assume W0 will be less than 1. But we'll assume W1 that the interesting regime is when W1 is bigger than 2. There, the network relies on the nonlinearities to stabilize the dynamic. Okay, but what happens then is something interesting, and this is what I want to begin the discussion at least. Okay, so
It's just when it's bigger than 2, or also when it's less than 2?
when W1 approaches 2, the system, is still stable, but is approaching the point of instability. And then as long, you can always take H1 to be small enough and so on to make sure that you always are in the linear regime. And that will be fine. So that will depend on H0 or mostly H1, right? In principle, the system can still be in the linear regime if W1 is below 2. But when W1 is above 2, independent of what H0 and H1 are, the system is unstable. Okay, so we're now asking what happens when W1 is above 2. Okay, the linear system is unstable. Okay, so we have to go back to the equations that I erased, or maybe they are here. No, I erased, and solve them, and find out what happens. But it's a very illuminating and very important for applications to look at the following case. Suppose H1 is 0. So I'm now going to assume so this is stationary linear, so I'm going to assume 3, a nonlinear regime, so this is 3, and 3a will be H1 is 0. What happens in that case? Okay, so I'm looking at the case where W1, the spatial modulation of the recurrent interactions is strong. Okay, that's what I mean strong when Talia asked me, or Tamar, what I mean strong. In this case, it will be just bigger than 2. Well, 2 has some units depending on the biophysics, but let's say 2 in our case. And but now I'm asking, what happens is H1, when W1 is close to 2, this is small, so a small H1 already will generate big A1. Now, when W1 is bigger than 2, we can ask what happens when H1 is strictly 0, which means that the external input is uniform. Now, what happens in this case? Well, naively speaking, I would say if the external input is uniform, then the network will converge into a uniform state, because all the external input are the same. All neurons receive the same external input, and so on and so forth. But it turns out that precisely because of this instability, the uniform state is unstable. Okay, because you can easily see it. If the system is uniform, then